Okay, great. Can you all hear me? Helmut, can you hear me?
Yes, I can hear you.
Okay, this still works. That's wonderful. So welcome everyone to this afternoon's distinguished Rothschild Lecture. It's my great pleasure and honor to welcome and introduce Helmut Bölcskei, who is giving this distinguished lecture in our Isaac Newton program on the mathematics of deep learning. Thank you so much, Helmut, for already returning to the INI today for the second time, because this morning Helmut already gave another talk in our seminar series. So before I hand over to Helmut, I would just like to say a few words about Helmut and his contributions to the mathematics of data science in general. So Helmut Bölcskei is professor in electrical engineering and mathematics at ETH in Zürich. In his research, he made fundamental contributions within the areas of information theory, mathematical signal processing, machine learning, and statistics. For his contributions, he was awarded several prizes and honors, really too many to name them all. And actually, Helmut asked me to be a bit briefer now. So just to name a few, Helmut has been the recipient of the 2001 IEEE Signal Processing Society Young Author Best Paper Award, the 2006 IEEE Communication Society Leonard G. Abraham Best Paper Award, and he has been awarded with the ETH Golden Owl Teaching Award. He is a 2011 EuroSIP Fellow, and he was a distinguished lecturer of the IEEE Information Theory Society from 2013 to 2014. He was also the recipient of an Erwin Schrödinger Fellowship from 1999 to 2001 of the Austrian National Science Foundation, and he was included in the 2014 Thomas Reuters list of highly cited researchers in computer science. He was an editor-in-chief for the IEEE Transactions and Information Theory, the TPC co-chair of the 2008 IEEE International Symposium on Information Theory, and the 2016 IEEE Information Theory Workshop. And he served on the board of governors of the IEEE Information Theory Society. So as you can hear, Helmut is a very, very distinguished researcher, and it's really an honor that he accepted our invitation to give this distinguished Rothschild lecture today on the mathematical universe behind deep neural networks. And I hand the word over to you now, Helmut.
Thank you very much, Carola, for the most generous introduction. And welcome, everyone. Good afternoon and good morning to those in the US. It's a pleasure and an honor to give this talk. And I'm deeply sorry not to be able to be in Cambridge. I have tried, but as you can guess, it's become very difficult. So what I would like to do this afternoon is I would like to take you on a journey of stargazing. So we are going to gaze at mathematical stars in the context of deep learning. This is joint work with a number of people: Leandro Eberhardt, Dennis Elbrechter, Philipp Gross, Recep Gül, Clemens Hutter, Gitta, who is also here, Philip Petersen, Dmitro Perekostenko, Werner Vlacic, and Thomas Wiatowski, many of them my former students, postdocs, collaborators. And I also got help with slides from Recep Gül, Dmitro, Werner, and Thomas. All right, so I said I would try to get the audience to interact a little bit. So this is going to happen now. So if you either use the chat or try to talk, I would like to start by reviewing some of the applications that deep neural networks excel in. So let's try to start with classification. And there is here a classification task. There are 4 people that, and we have 1, 2, 3 images for each one of them. Can you help me? And surely if a neural network can do that, you can also do that and help me classify those people. Any suggestions? Just speak freely. There's nothing on the chat. You surely must recognize some of them. Don't think mathematics only. All right, so I see something in the chat. John von Neumann, excellent. Thank you very much, Ira. De Herbert, funny, thank you. Funny, you're out for the next task, okay? Herbert von Karajan. Kurt Gödel, Hans, thank you. And the last one, this is for the Austrians. Actually, no international, but probably the Austrians will recognize. Who's the lady? That would be Elena Garancha. Good. Let's move to the second task. So this is not for funny, for everyone else. Annotation of images. So you present a network with an image, and the network comes up with a text describing the content of the image. Is there anyone who can help me annotate this image? Ah, very good, Hans Kleiber. Yes, so it's Carlos Kleiber conducting which orchestra? New Year's concert. Yes, which orchestras? Well, that's obvious, right? Vienna Philharmonic's New Year's concert. And now here is for the aficionados. He conducted it twice. So of course I know if Charlie Gröchnik would be here, I think he actually succeeded in this task once before. Does anybody know which year? Any guesses? All right, maybe Fanny. Fanny, would you know? No, okay. Not sure. All right, good. So that would be 1989. Okay, let's continue. So what else? CNNs beat the Go World Champion Lee Sedol in 2016. And then just recently, I'm sure many of you have read about the tremendous success of deep neural networks in protein folding, determining a protein shape from its amino acid sequence. So what I would like to do is I would like to visit a few areas of neural network theory and mathematics, and we'll just gaze at the stars. We're not going to dive deeply into the technical details. I will try to give some, but essentially try to tell the story. I would like to quote Ingrid Dobschi, who said that it's the guiding principle of many applied mathematicians that if something mathematical works really well, there must be a good underlying mathematical reason for it, and we ought to be able to understand it. Okay, so here is the definition of a neural network. It's essentially a concatenation of affine mappings and nonlinearities. So in each of those layers that you can see depicted on this picture, so you have inputs, those are input variables, 4 in this case. So in going from the green layer to the first blue layer, you perform an affine transformation, AX plus B, and then element-wise application of a nonlinearity. And then in the end, you linearly combine your last layer outputs to get the output of the network. So it's nothing but that, a composition of W's that which are affine transformations and rows, nonlinearities that act component-wise. So it's of course a highly nonlinear transformation. And I would like to point out in terms of notation a few items. M is the connectivity of the network, the total number of non-zero parameters in those affine transformations. L is the depth, the total number of layers, and W is the width of the network. So it's the maximum of the number of nodes across all layers. So those are parameters that we will be using throughout the talk. And here I think is a good place to, I have two essentially guiding themes or two things I would like to convey. First of all, this talk in many respects is going to be about universality of neural networks, not only in the sense of Hornig and Sibenko, as I will review in a second, but you will see universality in very different guises. And what is the mathematical reason for these strong universality properties is the compositional structure. So classically, we have been working a lot, especially in approximation theory, harmonic analysis, with dictionary representation. You try to represent a function as a linear combination of dictionary elements. This is a very different structure here. It's a compositional structure. I see a question in the chat. Yuri, are the slides frozen? No, maybe I just spoke too long about this slide. Can you see the next slide? Kolmogorov, Donohoe universality. Yes, it's okay. Thank you. All right, good. Okay, so here is the first topic I want to cover. Fundamental limits of deep neural network learning. Now, what we can ask ourselves is the following. what is it that we can do at best with a deep neural network in terms of which function classes are learnable at all? If we ignore the fact that we have to have a learning algorithm, and if we assume that we have full knowledge of the function to be learned. So of course, we are shaving off two of the major challenges in neural network theory. We just want to try to understand what is possible. So this is, if you like, an information theoretic view. What are the fundamental limits in representing functional relationships through this compositional structure? And the 1989 seminal paper by Harmonic and independently and at exactly the same time by Sibenko told us that a single hidden layer neural network. So if you remember the picture, we have an input layer, then there's one hidden, i.e. blue layer, and the output layer. So if you just have one hidden layer, they showed that essentially every continuous function can be represented as a neural network to within arbitrary accuracy. It's not a quantitative result, so there's no bound in the number of nodes that you need. So this line of work came later. Andrew Barron was one of the pioneers in this area. And there's some more recent work also along those lines, no bound on depths and so on. So the point I'm trying to make here is that most of these results are not quantitative. So the question is, can we develop a systematic framework? Can we be quantitative, and can we say something about the complexity of the approximating networks as a function of the complexity of the hypothesis or the function class that we want to approximate? And the answer will be yes, and we're going to use Kolmogorov, Tikhomirov metric entropy, and the framework that was developed by David Donahoe in the early 1990s. So deep networks, that's the first thing I would like to show, provide exponential approximation accuracy for a wide range of functions. So, okay, it looks like there is a piece of another slide hiding the current slide. Is that the case? Or Carola, can you see the slide well?
The slide well.
Yeah, okay, good. All right, so maybe not anymore, but it was for a moment. Okay, good. All right, so let's start. One of the simplest functions you can think of is the squaring function. Can this compositional structure approximate the squaring function? And if yes, how complex does the network have to be? And so here is a beautiful result by Dmitry Yarotsky that really started off much of the work that happened in approximation theory in neural networks, who showed that the squaring function can indeed be represented through this compositional structure with the finite width network and the depth of the network scaling like logarithm in 1 over the approximation error. Now, if you take it from here and you say, well, and I will show you on the next slide, some kind of algebra, how you can generate based on the squaring function and the multiplication function, all sorts of functions, but the basic statement I want to convey here is that if you have a finite width network with depth scaling polar logarithmic in 1 over epsilon, then it turns out that the connectivity of the network is upper bounded by the number of layers times w squared plus w. W is the width. So in each layer, we have an affine transformation. The size is at most number of non-zero entries, and the matrix is at most w squared. Matrices are at most w by w, plus w for the bias vector. If you rewrite this and you replace w by a constant and L by log 1 over epsilon, you see that the approximation error decays exponentially in the connectivity. So individual functions can be, at least the squaring function, can be represented in this compositional structure with an error that decays exponentially in the number of real valued parameters in the network. How do we go from the squaring function to more general functions? Well, you build the multiplication function by realizing that xy can be written in the form as displayed here. Now, x plus y, a linear combination, this you can easily realize through a neural network. It's an affine transformation. And then you already have the squaring network. And then you have the difference of 3 squares, which is a linear combination of outputs of squaring networks. You put those networks in parallel and you get the multiplication function. And you, I'm sure, get the idea already. Once you have the squaring function, you have the multiplication function. You can realize polynomials. If you have polynomials, you get the Stone-Weierstrass continuous functions. And you can also realize oscillatory functions through Jarodsky's sawtooth construction, which I'm not reviewing here, but you can do Fourier series, etc. And then you take it from there. So that's the neural network algebra that allows us to realize individual functions with exponential error decay. Now, function classes. If you try to learn from a hypothesis class, you have a whole class of functions. And the question is, how well do neural networks do in terms of learning functions from a function class? So a function class for us is going to be a compact set C in some ambient space. This could be a Bezoff space. It could be a Feichtinger-Gröchenig modulation space. It could be a Sobolev space, smooth functions, whatever you have it. How does the complexity of a network approximating all elements from this set C scale or behave as a function of the complexity of the function class? So how do these two complexities relate to each other? In order to be able to answer that, we are going to quantize our networks. What we mean by quantize is that the weights are no longer going to be real numbers. They are going to be taken from a finite set so that we can represent them with finitely many bits. So the bottom line is we are trying to see whether there is something hidden in each real number being representable by infinitely many bits, and the answer will be no. So we want to be very concrete, and we have a certain bit budget for each of those real numbers. That will allow us to describe the network as a bit string, uniquely decodable. One part encodes the topology, so where the connections are in the network, the non-zero weights, and the other part encodes the quantized weights. And the statement that I want to make here is that deep neural networks are actually universal Kolmogorov-Donohue optimal approximators. What I mean by that is that, as I just said, we view the network as encoding a function. Different topologies and different quantized weights correspond to different input-output relations, and these different input-output relations correspond to different functions. So the question is, what are the coverings that we can construct with deep neural networks? And are they optimal in the Kolmogorov-Tikhomirov sense, or if not, how far away are they? Can we construct or get optimality for a given function class, for more function classes? And the answer will actually be for anything out there you can possibly imagine. Let me briefly say that we care about the number of bits that we need to describe a neural network that represents or approximates a given function from within a function class to within an error epsilon. And so this exponent gamma here, you can think of it as quantifying the description complexity of the function class. If gamma star of C is larger, then you have a smaller growth rate and smaller memory requirements. So large gamma is good. But it won't play too much of a role. I just wanted to raise awareness for the importance of this exponent. And those of you who work with metric entropy will see that it's related to Kolmogorov's optimal exponents. And you see here this order epsilon to the -1 over gamma. So you will recognize this from metric entropy theory. Good. So classically, we approximate functions from function classes as linear combinations of dictionary elements, wavelets, Weil-Heisenberg frames, local cosine basis, Fourier basis, whatever you have it. Never mind all the clutter on this slide. This is just to define that classically what we do is we have a dictionary. We say we have M dictionary elements, and we want to represent our function as a linear combination of those M dictionary elements. We allow the dictionary to be infinitely large. However, we have a constraint on how deep we can search into the dictionary. This is this pi of m, a polynomial depth search constraint. I don't want to spend more time on this. And the coefficients are quantized. So we encode the function f by encoding in binary format the indices of the participating functions in the dictionary, the participating wavelet elements, and the coefficients ci that are quantized. And because they're quantized, we can represent them in bit strings. Okay, so what are the limits on that? So gamma star effective of C, D tells you how well you can represent a given function class C in a given dictionary D. Now, this exponent is going to be upper bounded by the Kolmogorov exponent, so you cannot beat the metric entropy limit. So Kolmogorov tells you what the minimal covering is. You cannot exceed that minimal covering. What is interesting, though, is to find out which pairs C and D achieve Kolmogorov optimality. So in other words, if we want to know for a given function class, what are good pairs or good dictionaries that allow us with what is called best M-term representation to get Kolmogorov optimality. The following incomplete table gives you an idea. So, for example, you have a Bezoff space, so these are all unit balls in the ambient spaces. Bezoff space wavelets have long been known to be optimal, and on the right-hand side, you see gamma star of C, which is S. Now, in square brackets, just to make the case that the dictionary matters, if you use a Fourier dictionary in a Bezoff ambient space, the Bezoff ambient space somehow has the structure of the affine group. If you use a Fourier dictionary, which has the structure of the Weyl-Heisenberg group, you're going to get an exponent that is strictly smaller, namely S minus 1/2. If you use a Feichtinger-Gröchning modulation space, then the optimal dictionary are local cosine bases or Wilson bases, and you get this gamma star of C as 1 minus 1/2, sorry, plus 1 over P. And then you see all sorts of other spaces. I think the key message here is simply to convey that given a function class, you should actually know something about its structural properties. Then you can pick a dictionary. And if you make a wrong pick, you won't be able to get Kolmogorov optimality. So this is a big field. Much has been published and studied in terms of what are optimal pairings. But the bottom line is you have to make a pick and you have to know something about your hypothesis class. Now, often in practice, this knowledge is difficult to come by. And so the question is now, can we do something smarter with neural networks? Or how would we think about approximation neural network theory in general? So what we do is we replace this idea of best M-term approximation by best M-weight approximation. So we allow M non-zero weights in the network. We interpret the neural network as an encoder and evaluate it in the Kolmogorov-Donohoe framework. And as already mentioned, you need to encode the topology and the quantized weights. And the question is, how many bits do you need relative to the Kolmogorov limit? And the answer is given by defining this formal concept of effective best M-weight approximation. And again, never mind the details. It's like before in dictionary approximation, but now the number of dictionary elements is replaced by the number of connections that are present in the network or the number of weights. And well, you see here that now if you look at the theorem statement here, that we have gamma neural network star effective of C. So this used to be gamma of C comma D. So for a given function class C, there was a dictionary D, and this gamma star effective of C comma D told us how well they fit together. Now, just think in terms of the following replacement. The dictionary is replaced by the neural network. And there's only one structure, it's the neural network structure. We're no longer going to try to match the dictionary to the function class. We work with a given function class C, and we have neural networks, and we train them, and we have a Gini-based training algorithm. We have all the data in the world. And the question is, for which function classes C can neural networks achieve the Kolmogorov limit? And as a byproduct, in answering this, you also actually get the result that tells you that if you want a neural network that achieves an epsilon worst case approximation error within your hypothesis class, then the connectivity has to grow at least according to what is here at the bottom of this slide. So you cannot beat the Kolmogorov limit. That gives you an idea of how large your network has to be so as to stand a chance to get an epsilon approximation error. Anyways, but the key question is, what are good function classes that are matched to neural networks? And the answer is, all of these function classes that you have seen before are universally optimally approximated by neural networks. So in other words, the task of understanding something about your hypothesis class and choosing the matching dictionary is no longer an issue. You train your neural network. If you train it well, if you have enough data, you in principle can achieve Kolmogorov optimality for all these function classes here. and many more. So this is just a small sample. And what is remarkable here is, as I mentioned before, so Bezoff spaces, wavelets have the affine group underlying, modulation spaces have Wald-Heisenberg group underlying. So these are two very different group structures. And you can see how the affine group structure is somehow a good fit for neural networks because we have affine transformations followed by nonlinearities, etc. But the Wald-Heisenberg group structure, time shifts and frequency shifts, this is much less clear that you can also optimally realize this with a neural network. All right, now can we do something with neural networks that you can't do classically, or at least that was not known yet how it could be done? And here we picked two examples, oscillatory textures according to Laurent Demanet from MIT, and the Weierstrass function, continuous everywhere, differentiable nowhere. So these functions are known to be very hard to approximate, and the best methods to date were of polynomial accuracy. So no methods were known that achieve exponential accuracy. Now, for those of you who work with fractals, you will probably see, well, if you have a fractal generated by an iterated function set, so you have an affine transformation like the Cantor-Middle third set. You have 1/3 x as one function and 2/3 plus 1/3 x as the other function, and you keep composing these functions. Now, if you have a Rayleigh nonlinearity, it can realize the identity mapping very easily as rho of x minus rho of minus x. So you can see how iterated function systems can be realized well with neural networks. But anyways, the result that you get is that deep neural networks approximate oscillatory textures and the Weierstrass function with exponential accuracy. The latter result was extended later to more general fractals, namely those of iterated function system type by Dobzhidovor and Hanin. So that brings us to the end of the first part of the talk. And let me briefly summarize which mathematical stars we gazed at. We didn't visit them and look at them in detail. So it was approximation theory, functional analysis, abstract harmonic analysis, frame theory, fractals, and metric entropy. I would like to switch gears and talk now about a different neural network structure and a different application, namely feature extraction. So very often neural networks are used as the first step in a classification procedure. So you try to extract relevant features from images, from speech, from audio signals, and then try to classify your underlying images or whatever you have it based on those features. The question is, why would we want to do that, and why would we want to have nonlinear feature extractors? Well, if you have these two categories of points, blue and red, and you're given a task of classifying them through a linear classifier, essentially a hyperplane that you can have passed through the origin or with an offset somewhere, so a line here. Of course, that is not possible. However, if you apply a feature extraction, meaning you transform your points, which we call f, by mapping them according to the norm of f1. So the norm of f, I mean, you just look at the radius of these two circles here, and then you get all the blue points to map to this blue point and all the red points to map to this red point. And this is actually very easily linearly separable. Now, what I would like to have you look at this in terms of invariances. Why? If you look at all the blue points and all the red points, what we have here is an invariance with respect to rotations. Now, in practice, often invariances are, so phi is invariant to the angular component of the data. In practice, invariances are often in neural network theory or machine learning in terms of shifts, and I will be more specific about it later. So if you have handwritten image recognition, if you write a 3 at the top left of your page or at the bottom right, it shouldn't matter, right? So you should have translation invariance. That's why invariances are important. Now, a second item of importance here is we want to have a trivial null set. So we don't want any features to map to the null function. So there's a question here. In which norms is this exponential approximation So there's, I mean, L-affinity, L2, there is all sorts of results, and the Hornig-Sebenko theorem has been extended by people to all sorts of different norms, etc. So I'll be happy to send you references offline. Good. So you don't want to have a function f mapping to 0 through feature extraction, because you will lose those features and they won't be classifiable. All right. So here is this issue of invariance and covariance. So I mentioned that we have angular rotation or rotation invariance before. I mentioned handwritten image recognition or digit recognition, the 3. It shouldn't matter where you shifted in your image. But invariance is not the only thing in feature extraction. Sometimes you want to have covariance. Why? Well, if you do face recognition, it turns out that the distance between the eyes and the nose and the mouth is actually a very important feature that helps you recognize images. So you want to preserve distances, and you want your feature extractor to tell you something about the relative distances of certain features. So we have both invariance and covariance towards shifts, for example. So if you continue, then you want a certain deformation sensitivity or robustness. You have a picture here of what is likely the most famous Swiss mountain. And if you take the picture with an older or a newer camera, there's certain deformations. So you would like to have certain robustness. And clearly, if you look at these two pictures, I'm sure all of you will recognize the Matterhorn on both pictures, also on the right-hand side. Good. So in summary, we have invariance, covariance. We have this null set property. I call it null set because it's nonlinear transformations. We have this deformation insensitivity, and these are the issues that we expect from our feature extractors. And once you have extracted your features, you pass them into, let's say, a support vector machine, and you perform classification. So now what is the network structure I would like to tell you about? It's known under the name of scattering networks, pioneered by Stéphane Malin in 2012, who had the following idea. He said, well, let's have an input signal F. Let's use a wavelet transform. So the G's here are wavelets, or you have a mother wavelet and you have different time shifts and scalings. And let's actually convolve F with a wavelet function. Let's apply a specific nonlinearity, namely the magnitude function. And then we take at each node the resulting signal, and we filter it by a low-pass-like filter. And these wavelet filters and the Chi's, the low-pass filters, they together form what is called a multi-resolution analysis. Later, this was generalized, this structure, to arbitrary frames. So you can replace the wavelet by other structures. The idea being, again, that other structures like Van Heisenberg, ridgelets, shearlets would be better suited to other classification tasks. And the question that we want to ask is the following. For the mapping that maps the input signal F to the feature vector, which is the output of all of these nodes passed through filters, and these filters can be general. So what we are doing now here is we're trying to make the structure as general as possible while preserving the tree structure. So you have convolution, the nonlinearity need not be a magnitude, the filters need not be wavelets, and the Chi's need not be low-pass filters. So the idea is that we have a modicum of freedom here, and but yet we want a prescribed structure, this tree structure, so that we can semi-train this network by picking the right filters, the right nonlinearities. And there's also what is called pooling. Pooling operations are essentially averaging or subsampling. And the second result I would like to present here is, or the second statement I want to make is that it turns out that generalized scattering networks, so meaning no matter which filters you use here, which frames you use here, which nonlinearities, as long as they satisfy certain minimal properties, which pooling operators you use, it turns out that you can show that all these 4 desirable properties that I mentioned, namely translation invariance, covariance, small deformation sensitivity, and the trivial null set, they all hold irrespectively of the filters, nonlinearities, and pooling operations you apply, as long as your set of filters forms what is called the frame. Your nonlinearities are Lipschitz and your pooling operators are Lipschitz. And it turns out that the invariance that you get is something that is actually obtained by making the network deep. Namely, we call this vertical translation invariance. If you go deeper into the network, your features become more and more translation invariant. Closer to the root, the features are more covariant. And it indeed turns out, if your task is image recognition, then the features closer to the root will be more important. The classification algorithm will actually work with those features. And if you want something where invariance is important, then the features closer to the bottom are going to be important. And to get all these results, I don't want to go into all those details. All you need is your filters, your G's and your chi to form what is called a semi-discrete frame. And these filters can be structured, they can be unstructured, learned, unlearned, randomly picked, whatever you have it. The nonlinearities are pointwise nonlinearities. They should be Lipschitz. This is satisfied by virtually all nonlinearities that are used in the deep learning literature. And the pooling operation, averaging, subsampling, and so on should also be satisfying certain minimal properties. And in this case, there's also Lipschitz continuity involved. And then you get this deep translation invariance. And so closer to root covariant, further down you get invariance. Okay, now trivial null set. Yes, you can get it. For those of you who work with frame theory, you know that the frame lower bound guarantees you a trivial null space of your mapping, your operator that you use to map the signals to the frame coefficients. But here we have something nonlinear. So what is interesting is that it turns out that if your nonlinearities and your pooling operators are Lipschitz and you use a frame in every layer of the network, and by the way, the frames you use in the different layers can be different, that is sufficient to get an overall energy conservation property. So phi of f is this feature extractor, the mapping from the input f to the feature vector. And you simply go through the network, you pick up all the lower and the upper frame bounds, and you take the min and the max respectively. And that gives you an overall relationship that looks like a frame double inequality, but it's not, because it's a nonlinear transformation. In particular, if you use Parseval frames, or tight frames, in every layer, then you actually get full energy conservation, although this is a highly nonlinear transformation. And as a byproduct, you are guaranteed this trivial null set property. Okay, so what were the stars that we gazed at in the course of this part of the talk? Functional analysis, harmonic analysis, frame theory, operator theory, differentiable manifolds, and Sobolev spaces. You will have realized by now that I have some favorite stars that I keep visiting. Of course, this is owing to my technical background, but I'm going to try to move to a different part of the universe now and look at universal probability distribution generation. So I apologize to those of you who attended my talk in the morning for the repetition. What we would like to look at here is, in a sense, the reverse task to this. You remember this picture of Carlos Kleiber where I claimed the neural network can annotate the image. Now the reverse task is actually generation of information. If you look at this picture here, you'll see images generated by deep neural networks. These are not real people. These are images that were generated based on trained neural networks. There are other things you can do. So that's the actually the inverse operation to the Kleiber picture. You give the network a text. The small bird has a red head with feathers that fade from red to gray, from head to tail, and out come these beautiful pictures here of indeed birds that fit this description. And then there's photo in painting that you can do with so-called generative context encoders. And there's many applications of generative neural networks. So the question that we wanted to ask ourselves was, if you have such a generative neural network with very low dimensional input and a high dimensional output, why low in and high out? Simply because often in practice, like in natural language processing, this is what you get. The input of the network is determined by the dimension of what is called the word embedding and mapping from words to vectors in Euclidean space. This would be a dimension of 100. and the output layer represents a vector of probabilities for each of the words in the vocabulary, typically about 100,000. Moreover, if you have low dimensional input, high dimensional output, if you can keep the network small, meaning a low dimensional input, you get a more parsimonious network, and this will require less training, etc. And we want to understand what is possible at all. So here's the task. Concrete. You have a uniformly distributed random variable on the interval 0, 1. You pass it through a neural network with one input and two outputs, and you specify a target distribution. Can you realize every target distribution with a neural network? And if so, at what cost? How complex do the networks have to be? And again, you will realize that there is something related to metric entropy involved. The answer is indeed, you can show that any target distribution you can realize with a deep neural network. And in most cases, you actually do get this with a neural network of minimal size in the sense of metric entropy if you try to cover the space of probability measures that you're interested in. The way we do this is we first realize that if you push forward a U01 random variable through a ReLU network, then you have a piecewise linear function that is realized by the network, and you get a histogram distribution as the output. So ReLU networks cannot be expected to realize anything beyond histogram distributions, but I'm sure you've already seen the idea. You go now and take your histogram bin size to be small enough, and you get to your target distribution. What is interesting here is I marked this first step here as dimensionality increase. You actually want to go from 1D to 2D, and you have one random variable uniformly distributed, and you want to generate any target distribution. Question, can you extract enough randomness out of this single random variable to generate any d-dimensional target distribution? Answer, yes. And the way you can think about it is you think about the binary representation of a U01 random variable. You realize that all the bits are independent, they are identically distributed. And then you just take every other bit for the first component and the other bits in between for the second component, and you have two independent components. So that's a very simplistic way of looking at this. And just to tell you that there are space filling curves involved here, very special space filling curves coming out of what I call the Rothschild construction, ReLU network that realizes a triangular function and that you keep composing with itself. And what you need to do is, if you take the network to get deep, then this sawtooth function here becomes tighter and tighter, and eventually you're going to fill the entire two-dimensional chart here. What you do is, if you push forward single random variables through this network according to the mapping on top here, so x is the input, U01, gs of x is this function here, it turns out that you can actually get this optimal approximation, and it works because this Yarotsky construction has the space filling property. Okay, and then you have to be a bit more, you have to adjust what we call the paint plan and so on. So I don't want to talk about this. There's a few more technical issues. The main result here is that fix your target distribution nu. There exists a network, in fact, with quantized weights of a certain number of non-zero weights, a certain depth, such that the Wasserstein distance between your target distribution and whatever the network produces is upper bounded by a sum of three terms. The first term comes from the dimensionality increase that you have to conduct. So S is proportional to the depth of the network. If you take the network to get deep, then this first term can be made arbitrarily small. The second term comes from the histogram distribution approximating the target distribution. Take the number of bins large, then this term goes to 0. And the third term comes from the fact that we work with networks with quantized weights, again, because we want to understand how complex these networks have to be. And so if you choose the quantization level to be 1 over number of bins squared, then you can drive the third term to 0 as well, and you have your universal representation result. Now, the main conceptual insight here is the following. You can say, well, if I want a d-dimensional target distribution and I have d uniformly distributed random variables, why not just apply the proper function, the push forward, and get my target distribution? But you would have a lot of randomness in the input, namely d, And the question that we asked is, we want small inputs, we want small networks. And it turns out that if you use a one-dimensional input, this doesn't come at the cost in terms of Wasserstein distance relative to generating the target distribution out of the independent random variables. So you're not going to be penalized, provided you take the network to be deep. And to wrap this up, I don't want to go into the details. And again, forget the clutter here. What is the statement on this slide? If your target distributions are histogram distributions, then you can do all this Kolmogorov metric entropy optimally. And for more general distributions, you can do well, but we don't know whether it's optimal. But the bottom line is, the network encodes the probability distribution. How? Well, it's driven by uniform input 0, 1, and different topologies and different quantized weights generate different probability distributions. Those probability distributions are going to cover the space of probability distributions, and this covering is actually Kolmogorov optimal that you get. So let me review the stars that we have visited here: probability theory, rate distortion theory, quantization theory, approximation theory, and the theory of optimal transport. So the topic before the last, dynamical system learning. Now, what are the fundamental limits in learning linear dynamical systems? What we mean by linear dynamical system is actually the following. Think about a linear shift invariant system, or think about a linear time varying system, or if you like, even more abstractly, think about a linear operator. Can we learn linear operators? And I would like to emphasize that this is not learning, can we learn linear operators, i.e. can we learn PDEs, for example? So there's this class of pseudo-differential operators, and then the question is, can we learn those operators or the corresponding PDEs? We are not trying to learn the solutions of the differential equations. We are trying to learn the differential equation itself. So for example, for the electrical engineers, if you have an LTI system, can you learn or identify the LTI system from input-output traces? So you have input signals that you observe the output, you do this sufficiently often. Question, can you identify the system to within a prescribed accuracy? So what we are going to show is that indeed this is possible for a very general class of systems, and optimally so. And we're going to use a representation result from a harmonic analysis that you can find, for example, in Charlie Gröchenik's wonderful 2001 book on time frequency analysis. So you can write every decent, I put here, I don't want to go into details, linear operator as a weighted superposition of time and frequency shifted versions of the input. And this weighting function is called the spreading function. And the network structure we're going to use now, because we're dealing with systems and they have sequences as inputs and outputs, is that of a recurrent or a feedback neural network. So here is the formalization. And the first main result I would like to convey here is that every decent linear operator can be realized exactly with a recurrent neural network. And the way this is established, this result, is you use this representation here. Time shifts, I'm sure you see very easily how this can be done, but also frequency shifts can be optimally realized with a recurrent neural network. And then if you put everything together, that's how you get this universal realization result. The question is now, can we be more quantitative? And the answer is yes. And here I would like to make explicit the connection to differential equations. And I would like to do it for the simplest possible case. Namely, the systems we look at are linear shift invariant systems. So here are the difference equations, linear difference equations with constant coefficients. And those correspond to linear shift invariant systems with rational transfer functions. And well, we know already from the result that I just mentioned that they can be realized, these transfer functions, exactly with recurrent neural networks. It turns out, however, that this quantitative aspect, namely how many questions do you have to ask of the system, meaning how many input-output traces and how accurate do those input-output traces have to be to get to learn the system to within an error epsilon. And it turns out that for linear difference equations, recurrent neural networks actually solve the system identification task in a metric entropy optimal manner. So there is work from control theory by George Samers from the 1990s that we built on. If you don't know these papers, I highly recommend them. It's wonderful reading. Okay, good. So let me summarize the stars that we visited here. PDE theory, the theory of underspread operators as put forward by Charles Pfefferman in the early 1980s. Operator theory, metric entropy, Hardy spaces feature here. And I can, of course, not conclude without visiting the complex analysis star. I guess that would be a disappointment. So let me have as a last topic something that has little to do with universality, if at all, but touches upon a very basic question and then leads us to complex analysis and many other beautiful theories, namely neural network identifiability. What we mean by that is that if you're given a function and you realize it's through a neural network, the mapping from the function to the neural network architecture, is it unique, and under what conditions is it unique, or if not, how big is the source of non-uniqueness? What can we say about this? So there was, we are going to do this actually for the 10H nonlinearity. And there was a paper in 1994 by Charles Pfefferman, who established under a set of conditions, I believe it was 8, we call them genericity conditions, that neural networks N1 and N2 that have the same input-output relation and are based on the 10H nonlinearity, they are identical, the input-output relations, if and only if one network can be obtained from the other one by a series of sign flips. What I mean by sign flips is 10H is an odd function. So if you flip the sign of the input to 10H and the sign of the output, nothing is going to change. And it turns out that this is the only source of non-uniqueness. The architecture, apart from permutations, of course, of nodes, will remain unchanged. So that's the only source of non-uniqueness. And Pfefferman conjectured that you can do away with these genericity conditions. It turns out that these conditions have things like linear independence over the rationals and things like this. So somewhat elaborate set of conditions. And this is actually something that was just recently established, that indeed you can remove all these genericity conditions and you get actually the statement that we have just seen, that N1 has the same input-output relation as N2, if and only if one network can be obtained from the other by a series of sign flips. Now, this doesn't work for the Rayleigh nonlinearity, but because there are big null nets involved, so parts of the network that map to the null function, and then you cannot identify them. But for 10H, it does work. And just to conclude, give you an idea of how it's done, it actually records, so the 10H has this poles on the imaginary axis. So then if you have linear combination of different 10H functions, you get these different pole sets. And the idea is not to give you a proof here, but you start studying then as you go deeper into the network, then clusters of poles form around poles in the previous layer. And then you get very elaborate pole patterns and you study their density in the complex plane. And that's actually how the proof works. So the mathematical stars that we have visited in this part of the talk are complex analysis, the Bayer category theorem, graph theory, Weil's equidistribution theorem, dynamical systems theory, group theory, Lie algebras, Lie groups, representation theory. All right, on that note, I would like to close. Thank you very much for listening, and I'll be happy to answer any questions you may have.
Thank you so much, Helmut. Can you hear me?
Yes, I can hear you, yeah.
Okay, excellent. Thank you. Really, thank you so much for a wonderful tour through various mathematical aspects of deep learning. It was really great. Do we have questions? So we have one question already in the physical audience, but please, can I encourage everyone who is online to either raise your hand and then we will call you out to speak, or type your question into the chat. But I'll start with
thank you very much for a very interesting talk again, as this morning. I was particularly intrigued by these frame bounds, or Parseval type bounds in the nonlinear case.
Mm-hmm.
Could you say a little bit more about this, please? Does it hold in any sort of limit, and what are the details there?
Yeah, so of course, by default, I would defer to the paper. It's actually very lengthy and technical. I don't think I have a very good idea in terms of, giving you a lot of intuition behind these results, but the shape of the filters plays an important role. But and actually I should have mentioned that we work with Sobolev spaces here, so that also plays an important role. So the space structure, but other than that, you have to do a lot of grinding, and I fear there is no good intuition that I can give you here. It turns out that actually you have to study how the energy decays as you go through the network, and it decays either polynomial or exponentially in terms of the depths of the network. And this decay property has to do with analyticity of certain functions. So there's some complex analysis in there. Yeah, so it's a number of things, and of course we picked everything so that it works and fits together. But I agree, the final result is actually something that looks like what you get in the linear case, although it's non-linear. So I'm sorry I cannot give you like the one sentence idea, but I'll certainly be happy to send you a reference to the paper.
Yes, please do, and thank you very much.
You're welcome.
Great. Are there more questions here in the physical audience? Helmut, my laptop died, and so I can't see the Zoom. So Fanny, I think, raised her hand. That's what I can see. So Fanny, do you want to talk, to unmute yourself?
Yes.
Yeah, perfect.
So I just had a question regarding the different function spaces where you say you can be optimal in this approximation to the extent, or this exponent. So I was wondering if you also get a constructive proofs for how the weights, which weights would be non-zero. Can you see kind of a structure that corresponds to a particular function space? I was just thinking about convolutions, of course, in that sense. Like, could you uncover for certain types of function spaces, you will get a certain type of structure in the non-zero weights, or is there something you can see in your proof? Or
yeah. Yeah, right. So thanks for the question. I was actually afraid you would complain about me having shown Carlos Kleiber, but I'm relieved now that I think I can answer your question. So the proof works via a principle that we call the transference principle. So what we do is we take a dictionary and we try to realize every dictionary element with a neural network. And if that can be done well, quote unquote, and you have a structured dictionary like a wavelet dictionary. So let's suppose you can realize the mother wavelet well, then all the other wavelets are realized well because, well, you get them by affine transformations, and affine transformations are easily realized. And then the idea is that when you look at these neural network realizations of the dictionary elements, then these dictionary elements should have a property that makes sure that these neural networks don't get out of control in terms of their size. Then you put them next to each other, all those participating dictionary elements, you form a linear combination. Each of them is represented by a neural network. Linear combination is again a neural network. You're done. The question that you asked, I guess, is, if I understood correctly, is when you go back. So for example, you have a hypothesis class that has an affine or a Van Heisenberg structure, and you trained a network. Will it actually learn a representation that looks like a dictionary approximation? And I think it's a super interesting question. It's an identification result. We have no proofs about this, but in the paper from, I guess, 2 years ago with Gitta and Philip Gross and Philip Peterson, in the last section, we had simulation results, very, very basic, with actually Richlets. And those results indicate that this may indeed happen, but I'm reluctant to say that it will happen, and under what conditions, I don't know. But if I were to try to prove this, I would try to set it up as a neural network identification result, akin to what I presented in the last part of the talk. But at least these examples, if you look at them, they indicate that indeed the network actually learns the dictionary and then puts everything together.
So by learning, you mean if you train it using some method, or in this case, when you say you simulate?
Right.
Okay.
Yeah, so we use gradient descent,
Okay.
and we picked a very highly structured function class or hypothesis class And then we got actually the corresponding, I mean, optimal dictionary. All I'm saying now is very strong. So if you just take away 10 dB, then that's essentially what we did in the paper. And you can look at the setup. It's somewhat contrived, but I mean, that was our idea at the time, to try to see if this indeed happens.
Okay, thanks.
Sure.
Okay, we have a question in the chat by Sarah van der Geer. Would you like to unmute yourself and ask the question, or would you like me to read it out loud?
Yeah, so.
Yeah, I just wondered, to what extent does this neural network theory replace dictionary learning, or is it, how's the relation? I mean, it seems that neural networks work for any dictionary. So that's what you're saying, right?
Yeah.
But what does it mean?
Yeah, right. Good. So thanks for the question. So
yeah, thanks.
I guess what I'm trying to say is that, of course, there's all these dictionary learning algorithms like Ellard's KSVD algorithm and so on. So we have not tried to compare. I guess this follows up on Fanny's question. We have not tried to compare how well neural networks do relative to those classical dictionary learning algorithms. But indeed, the idea is that the universality property tells you that if this identification result is correct, that neural networks, no matter what function class you present them with, and you may not even know what the underlying structure is in that function class, just take functions, throw them into a bag, and feed them to a good learning algorithm. If there is structure in the function class, the network will find it and it will find a good dictionary. It would be nice to be able to prove that. I think it's a great project. But yeah, I would not say that you know, we compete with dictionary learning algorithms and we can do better or things like this and so on. I wouldn't want to make that kind of statement.
Thanks, Helmut.
Are there more questions? Oh yes, there is one question by Hans Feichtinger. So please unmute yourself if you'd like to. Or I can read it out loud if Hans doesn't want. Okay. So Hans Feichtinger asks, doesn't depend on the amount of data available. There was no discussion of the time and amount of data to be learned, question mark?
Yes, indeed. So there is no, as I said in one of the first slides, we say we have a Genie training algorithm. We have all the data in the world. This is the best you know, you can hope for, and we just look at what is called the expressivity of neural networks. And that is actually, it's good that you asked me this question, Hans, because I had planned and forgotten in the end to say that we have not visited the universes of optimization theory, actually also not statistics. And this is something that we have not done. There is work by Johannes Schmid-Hieber, who has actually looked at regression with neural networks, etc. But learning from a finite number of samples, there is a recent nice paper by Philipp Gross and Felix Voigtländer that actually show if you have finite amounts of data, it's a tall order to get those nice approximation rates that we get. But I think this is just at the beginning, and there are certain people working on it. But yes, I totally ignored it. So that's why I use the word information theoretic approach. Suppose you have the best possible training algorithm with all the data in the world.
Okay, there is another question by Reinhard Heckel. Would you like to unmute yourself?
Yeah, okay, happy to. Yeah. So I was wondering, the statement on the scattering networks, they were irrespectively of the filters that were learned, and many properties were already somehow properties of the network itself. And so I was wondering, is a takeaway for practitioners of deep learning that the network structure itself is critical for performance, and that many important assumptions on the signals that we are learning and that we are working with are already built in successful architectures? Yeah,
right. So thank you for the question, Reinhard. Yeah, indeed. So all you need is you need in every given layer the filters, the G's, together with the corresponding extraction filter, the chi, that if you put them all together, they have to form a frame. And you know, it's very easy to realize frames. You can draw functions randomly, and you get the frame bounds to be bad potentially, but you can get the frame property. Good frame bounds matter actually for energy conservation, as we have seen. And indeed, nonlinearities and pooling operators, Lipschitz continuity, but the structure, this tree structure is important, and that indeed you pick out from each node the output and stack those outputs into your feature vector. So I would say a lot of the properties, that was actually the statement we tried to convey, invariance, covariance, deformation insensitivity, etc., is actually built into this tree structure that you have seen. And the fine details, of course, matter for practical performance, but these fundamental properties you do get already based on the tree structure, provided you satisfy these minimal conditions of having a frame, having Lipschitz nonlinearities and Lipschitz pooling operators.
Okay, there is another question by Sören Dittmar. Would you like to unmute yourself?
Can you hear me?
Yes.
Yes.
Perfect. So, given that we basically now have this recent hype around geometric deep learning, is the scattering transform simply a subset of that, or can we? Does it have additional value? So it obviously was there first. So, but now that we think or can think in terms of geometric deep learning, is there anything that the scattering transform gives us?
Yeah. So if you excuse me, can you? I mean, I think I've seen the term, but I wouldn't know exactly geometric deep learning. What exactly you mean by that?
The idea is to think about the deep learning in terms of robustness and invariance to, or equivariance, robustness, and invariance to a certain set of transformations. For example, for convolution, it's the transformations that you have shifts. So it's actually a group. So you want to be equivariant to shifts, and that basically gives you, okay, you should do convolutions.
Yeah, okay, now I know. I think I knew this, so thank you for clarifying. So what you call equivariance, actually I called covariance, and I showed that in image recognition, in face recognition, you want this covariance or equivariance. So I mean, the scattering networks have been around for quite some time. I've seen this recent work. I mean, you can see the scattering networks as simply as a feature extractor. It's a mapping, a nonlinear transformation from the input F to the output. And when it was first put forward by Stéphane Mallat, he was very interested in this. In particular, he was interested in translation invariance, and he got it by taking the wavelet scale parameter, or taking the discrete wavelet transform into a continuous wavelet transform. That's how he got shift invariance. And then he proved also deformation robustness, I should say, or stability. And then our question that we asked ourselves was, well, under what more general conditions can we retain these properties and potentially get even more? So I would say, well, if there is now interest in invariances and covariances and so on, these scattering networks, they give you certain invariances, they give you equivariance. But if you want a specific invariance, you need to tailor your network to that. And if you use wavelets, then you get a certain set of invariances. If you use Weil-Heisenberg, you get other sets of invariances, etc. So I would view them as a tool to generate feature mappings from an input to an output. And if you want to design them so that they have certain invariance properties, you have to tailor them. So in that regard, I don't think that one is a subset of the other or something like that, but these are feature transformers. If you go back to, there was actually in 1964, there is I think it's an absolutely outstanding paper by Tom Cover, who looked at, I mean, he essentially had found the VC dimension already. He looked at these nonlinear transformations, and I gave this simple example of these two circles here. So he tried to understand how many ways there are to classify points with nonlinear transformations, and he characterized them through algebraic varieties and counted their degrees of freedom. So that's how I view scattering networks, exactly as such nonlinear transformations in the spirit of Cover. So again, if you don't know that paper, it's Thomas Cover, 1964. I think it makes for wonderful reading.
Great, thank you so much.
You're welcome.
Okay, are there any other questions in the audience or in the chat? Okay, it doesn't seem to be the case. So with that, I'll take over the closing from Carola, who has some technical difficulties with her laptop and things. But we would like to say once again, many thanks to you, Helmut, for this wonderful talk. Very interesting and very inspiring, and also very rich in terms of the types of results you presented and in terms of the types of maths you used to obtain them. So let's thank Helmut once again. Thank you very much, and hopefully you can visit Cambridge in person next time.
Thank you very much to everyone for listening in, and I appreciate it. And I'm so sorry I couldn't be there, but I promise I will make up for it. And the first opportunity arises, I will come in person to the Newton Institute again. Thank you very much, and have a nice evening, and stay healthy and safe.
Bye-bye.
Bye-bye.